So you can introduce yourself and introduce the topic.
Great.
Okay, so let's start. Today, our meeting is with Professor Jacob Cybulski. Professor Jacob will talk about quantum autoencoders, which is strictly connected with our work. So, Jacob, floor is yours.
Thank you, Sebastian. First of all, I need to apologize. You're going to look at me sideways because I operate here a few different devices. Only my laptop managed to connect my camera and the sound. So I'm looking at the screen with the slide, and you can look at me sideways, but I'll be turning to you every so often. So apologies for this awkward position of the camera, and maybe the voice is not great. So welcome to the seminar on the development of quantum encoders. I'm Jacob Cybulski from Enquanted, Melbourne, Australia. And my colleague, Sebastian Zayans, who introduced me, is from SGH Warsaw School of Economics. And I'm going to walk you through the whole idea. What are quantum autoencoders? Why we are studying them? Why we're interested in removing noise from signals and time series, and then spent a lot of time talking about how you go about designing a complex model, and quantum autoencoders are such complex quantum models. Looking at the architecture of those models, spent some time talking about how you encode data, how you interpret measurements, how you design and consider the parameter space by the central part of the encoder, and then spend some time about the optimization, optimizers, training choices, and look at some of the results from Qiski Pendelane and PyTorch. So let's get into it. Let's first talk about what exactly is the problem we're looking at. A big question is, can quantum machine learning assist detection of complex patterns in time series and signals? And if so, how could that be done? And we have a lot of applications which are in this space. In fact, some years ago, I worked with an engineering company in vibration monitoring, in machine condition monitoring. Here is some sample signal from the machine. The dots indicate problem areas. There are applications in astronomical observations. I spent some time looking at forecasting of beer sales. So this is the USA sales of different brands of beer over time. But also, everybody heard about earthquakes, and seismological data is of interest to us, plus in health, like ECG, EEG analysis, identifying problems in people's health and heart attacks, but perhaps predicting heart attacks. So we are interested in all of this. And one of the issues is that all data in this space is temporal. It's time-based, and all suffer from some degree of noise and anomalies. And of course, noise is something we want to remove, and anomalies is something that we're interested in because they indicate some kind of a potential impeding failure. Okay, so all of this is very interesting, and that's why we're interested in analysis of time series using quantum machines. And why quantum machines? Because some of the relationships in time and space data are very complex. And even though time series analysis and signal analysis is a very advanced field, statistical methods and machine learning methods are being used. So we hope that there's something beyond the normal complexity that those methods could cope with. And this is where quantum machines could help, perhaps. So here's a typical problem. This is a fragment of data about beer sales. And of course, we're interested in predicting beer demand. And imagine that within certain brands, we have numerous manufacturers spread around the country. They all do their own predictions. They all specify what's going to happen in the future. And if you take all of those predictions into consideration, there is a lot of variations. And we could consider those variations noise. And of course, it's a valid spread of what projections you need to consider. And of course, there's a reality coming with time, and the reality will indicate what was the true behavior of your customers on the marketplace. So what we are interested in is somehow eliminate all those variants and variations, and a lot of inaccuracies, and somehow predict what is the baseline of all of this that is closest as possible to the truth. So we will try to do it in Qiskit, Pendelane, and of course, classically in tools like PyTorch. So this is the problem we're looking at here. And about myself, I'm the founder, researcher, consultant at Enquanted. I've set up this company only recently, so the website is still being prepared. For years, I worked as a professor, as an academic at various universities in Australia. And in the past, I looked at machine learning. I spent a lot of time in data visualization and immersive data visualizations. And the last few years, I'm really interested in quantum computing, and in particular, quantum machine learning, with a particular focus on quantum time series analysis and anomaly detection. In my private time, I do some recreational cycling, reading science and science fiction, and taking part in quantum challenges and hackathons, if my wife permits me every so often. I do undertake research collaboration with universities, and I supervise some research students, in particular in quantum machine learning. I do a lot of projects with Sebastian Zions, and this is one of the projects that we work together on. Now, some of you perhaps are not familiar with what exactly are autoencoders. So let me spend a few minutes talking about autoencoders and quantum autoencoders in particular. So autoencoders are deep learning models which take some input, then decompress this input into much smaller space, and then are able to decompress it back into the original form. And this is the technique used quite often with images, and also in signals, where perhaps the whole idea is that if we compress the information on input, that means some information will be removed and lost in the process. What we're hoping for is that the information lost is insignificant or unwanted part of this information, and the vital part of information will be retained. So if we, as input, put some noisy signal, if it's compressed and then decompressed, perhaps we're going to get clean signal where all the noise is removed. But also, if we remove a lot of unwanted information and we get something that is normal, if we compare it against the original signal, perhaps we could discover abnormalities such as anomalies, things which are out of ordinary and perhaps dangerous. So that's the idea of autoencoders. And in quantum area, autoencoders consist of two parts. There is something called quantum autoencoder and quantum decoder. So it's encoder and decoder. Encoder takes the original input and encodes it into the latent space, the space which is compressed. It takes much fewer qubits than the qubits on the original input. And there's a trash space of qubits which will be reinitialized. And this is where we lose information. And hopefully, we could train this model in such a way that all information of some importance will be channeled through the latent space of the qubits and will be decoded into a new form. hopefully as close to the original. If we could imagine for a moment that this is pure data on input, and this is some kind of a circuit which encodes this input some way. Let's assume the latent space is full qubits. If we invert the encoder, that means we create the adjoint of the encoder. That means automatically we're going to get the input and output, because the inverse of the encoder will simply cancel out all the activity of the encoder. So the signal will unimpeded appear on output. If we create now some barrier in the middle, of course, we're going to get some problems with the output. And in this case, we will be training the model to get as close as possible to the original input. And of course, you could train it by placing noise on input and clean data on output. And the parameters of the encoder and decoder could try to accommodate that during training, this transition from noise to pure data.
Okay,
we
Jacob, we have first question. Is autoencoding process kind of data cleaning? Is it used
so
for data
it is data
purposes?
cleaning, and classically, it's a filtering process, and engineers are very good at it. Okay, so in signal processing, electrical signal processing, and sound filtering, sound management, people do it all the time. Okay, so this is just a machine learning approach to something that engineers have been doing for years. So it's nothing new, and perhaps it explains why so few people work in quantum time series analysis, because the classic methods are so good. So we need to find a niche where the complexity of the patterns we want to deal with is very high. But we started with something very simple. So yes, I understand we have methods that people spend years on, and they're very good at it. So why we was looking at something like autoencoders? First of all, because, I'll talk to the ansatz in a minute. First of all, because time series, it's a massive data to start with. So we're going to take a part of it at a time, and we're going to look at a sliding window approach. But still, we have complex data on input, and there are floating point numbers flowing through the model. So potentially, we need to deal with many features on input. Potentially, that will require a lot of parameters in the circuit that we need to manage and train. It will be some kind of a semi-supervised method, because we're going to show examples of what we want to show on output, but this will not be a simple classification problem. It will be more like a regression type of a problem. And because of the complexity of the models that we're going to develop, there is a potential of the model getting stuck in training due to emergence of barren plateaus. So we're going to discuss some of those issues. And the model of like this is a typical complex quantum model. It's a representative of those complex models. And a lot of issues we're going to discuss today, you're going to find in other quantum models which have some level of complexity. So I'll get to the ansatz in a minute. There is this term here, ansatz. Ansatz is a parameterized circuit. And I'll show you examples of such circuits. In German, ansatz means method, basically, but the whole idea is that it's a trainable parameterized circuit. Okay. And another question, what's the latent space? It's a hidden space that we know it exists. It's hidden from input and output. And it's a space where in terms of machine learning models, this is where the information is kept. And in our case, this is where compression is taking place. So there's much fewer qubits reserved for the latent space than the qubits on input and output. How information is lost? Basically, because we put the barrier in the middle of the circuit, of course, there is some redundancy in information on input, but the greater is the barrier, it will force the loss of some information. What we want to achieve is that we lose information which is unwanted and want to keep information we're really interested in. Okay, let's start with the first issue. How do you encode data in a quantum model? Of course, quantum models do not take input as such. You need to hard code input into the circuit. And then the circuit is executed, and the results of putting that input through the circuit will be measured on output. And then if you want to have a different input, we need to create another circuit. And this is usually a very quick process. And hopefully the circuits are structured in an identical way. And if the circuit is executed on a quantum machine or the accelerator, they deal with identical structures. So it's easy to apply the structure to different types of input by joining matrices. So in general, the quantum model's input and output, in our case, when applied to signals and time series, it's a collection of real values. And this guides our selection of data encoding methods. One of the most common methods is basis encoding. That means the qubits act as bits of the encoded number. So we have a binary representation of number, and the qubits 0, 1s are encoded on input, hard-coded into the circuit as either gates X or nothing, and we have a single integer number encoded on input. That's not good for us because we want to deal with floating point numbers, real numbers. There's another approach called QRAM encoding, where all possible inputs are known in advance. They could be pre-coded in the circuit, and then we could refer to them. And again, this approach is not particularly applicable here because we cannot predict what type of values are going to appear on input in a time series. Now, the approach we are really interested in is the angle encoding and amplitude encoding. The angle encoding, it uses the state of a qubit, and the value is encoded as an angle which shifts and rotates the qubit space, either in X or Y axis. And the rotation is between 0 and 2 pi. In our case, we restrict it to 0 and pi. And of course, they are floating point numbers. Of course, you can't get perfect precision here because of noise, which will interfere with precision in a calculation. So in our case, if we consider here, we have X, Y, and Z axis on the block sphere. The y-axis is pointing towards us. If we want to represent the value from 0 to pi, we could represent it numbers like -1 to +1 by showing the rotation up or rotation down, and that changes the state of a single qubit, and we could encode as many numbers as there's qubits, and then perhaps we could also use rotation in x-axis. So we could easily double the number of encoded numbers in qubits. It is possible also to overload the circuit, and that means have a special technique where we re-upload numbers and we encode numbers in one after another and hope that interference could be brought to the minimum. But angle encoding is very popular, and it gives you a lot of flexibility. So this is the approach we use in our quantum autoencoder. There's something called amplitude encoding, and it's probably the least understood, the most feared technique. Is this one of the most useful encoding schemes? Very attractive to quantum autoencoders, where the input and output could have the same way of representing numbers. The way it works is that we encode the values on input the way we could be measuring those values on output. So if you consider the measurement of the circuit, here it is. This is some encoded amplitude encoding. If we measure the circuit, there's 2 qubits, we're going to get 4 possible combination of answers. So it could be measurement of 0, 0, or 0, 1, 1, 0, 1, 1. And in those measurements, if we repeat the measurement many times, we're going to get some kind of expectation values appearing on output. And those expectation values are the actual values that could be encoded and represented of what happens on input. So that's the whole idea of amplitude encoding. We encode the numbers, which are represented as those bars, the height of the bars. And if we measure it straight away, we're going to get on output exactly what was encoded on input. And then there is a special techniques for that, and each of the quantum languages has a method, an API, which does it for you. And usually it does it at the beginning of the circuit, around in the middle. And there's lots of issues with that. One of the issues is that in penny lane, for example, where a penny lane computation is every part of the computation needs to be differentiable, that circuit is not differentiable. It can't actually calculate gradients with it. The second issue is that when you do encoding of a particular number or series of numbers on input, that representation generates a slightly different circuit, which means that depending on the input on the values on input, we have different structures of the circuits. That is not going well with running those circuits on GPUs or QPUs. So for that reason, we had to give it up. But we are quite happy to use this encoding technique if we run our calculation on a simulator. Now, how do we measure and interpret results? Okay, so those of you who executed quantum circuits, of course, you have a dilemma. Should you measure all qubits or 1 qubit, for example? And it's, usually, if it's a simple answer you want on output, like a single value or a binary value, if it's a classification, measuring 1 qubit is good enough. If this is something like quantum autoencoder, we want to measure as many values as are represented in a window that we are processing, the window of the time series. So we need to measure all of the qubits. But it's all relative. If we wanted to measure a binary value, then we could measure a single qubit. And of course, the result of the measurement would be 0 or 1. If you repeat this measurement many times, the height of the bar could indicate which of those values is more probable, and that could be the outcome of your binary result, 0 or 1. If you want to measure an integer, that means we have multiple measurements. We repeat measurement many times, and we have the results, possible results appearing on output. It's a distribution of expected values. And now we can, if you expect to measure a single integer value, what we can do is to get the highest, the most probable outcome, and the combination of possible outcomes, 0, 1 across qubits, could give you the representation of an integer that you get on output. Or alternatively, what you can do is to get a floating point number, which is represented by the probability of this particular value appearing on output. Or we could take all possible outcomes and look at the probabilities as a distribution of values, which gives you a range of floating point numbers. And there's a lot of ways of interpreting results. Even, for example, and that's quite common, instead of measuring a single qubit, which actually, if you measure 1 qubit, that doesn't give you during training a good distribution of parameter values because it's all biased to a single qubit result. So it's always good to measure as many qubits as possible. That means a lot of things are happening throughout the qubits in the whole width of the circuit. But then you have measurements of individual qubits, like here. And what happens is what we can do is to consider the parity of different combination of outcomes. And if the parity is even, we could consider the outcome to be 0. If it's 1, we could consider this to be 1. And in this way, you could actually get a binary outcome by measuring all qubits. So this is the black art of measuring and interpretation of circuits. And you have many more possible things in between, like in time series analysis, if you want to predict value what happens the next week of sales, or 2 weeks or 3 weeks, you could split the outcomes into sections and have horizon 1 outcome, horizon 2 outcomes, and so on. So lots of flexibility. The thing is that it's not so easy as it is with classical programs, but it's manageable. Now, what happens in between? So we encode data on input. We can measure and interpret the results. And in between, we have the ansatz, the processing part of the quantum circuit. So here it is. This is actually the notation from Pendelane. So, that was the scheme which was adopted in Qiskit. At the moment, I spend more time with Pendelane than Qiskit. I was a bit upset with Qiskit because Qiskit became the product in a flux, and the versions were coming one after another. And it was a very volatile development around version 1 of Qiskit when IBM took over from the open source community. And at that time, I could not reproduce my results from the week before and the week after, so I moved to Pendelane. But I love Qiskit as a platform, and I spent a couple of years working with Qiskit. So here is ansatz. This is actually the whole circuit here. So we have some input block, which represents the value of the time series window on input. We have an output block, which has measurement and some pre-processing if required. And there's a middle part, which is the latent space, the qubits which allow the information to go through. And the trash space, the qubits which will stop the flow of information. And in Pendelane, this is done by measuring each of the qubits and then reinitializing the qubits to 0. In Qiskit, this could be done simply by initializing qubits mid-flight. So a lot of developers of quantum platforms, they spent a lot of time on that mid-circuit measurement, because measurement is a very slow operation, and to make it useful to programmers, you need to literally deal on a hardware level how to make it efficient. But nowadays it's available on most of the platforms. So this is the middle part. So in this case, we have the latent space, which is about, we have 5 qubits to encode input and output, and 2 qubits are trash, 3 qubits are latent space, and if needed, we could add more qubits. If we don't needed to have more parameters, we could add qubits which have nothing to do with encoding and decoding of information, but they give you extra parameters and extra entangling between the qubits in action. Now, this represents the quantum autoencoder, the encoder. This is the quantum decoder, encoder into latent space, decoder from latent space. And those blocks could consist of many layers. And each layer would have the rotation block, the parameters, which are trainable. There's an entangling block, which entangles the qubits in some predetermined way. And then we could have multiple blocks. And again, the rotation block, entangling block, and so on. And this decoder could have a mirror of what happens on input. The mirror, if we wanted to simply have identical inverse as possible, but normally would have a different set of parameters here, so that the trainable parameters are embedded into the encoder and decoder, and the more parameters we have, the more difficult to train. So that's the circuit we're dealing here with, and needs to be optimized. The parameters need to be optimized so that given specific pairs of input and output, we could train this circuit to perform the task. The task is either to mirror what happened on input onto output, or do so and remove noise in the process. And the choice of optimizers. Okay, so we have, when working with Qiskit, when you try to use the gradient-based optimizers, the optimizers which look at the geometry of the space of the loss function, and we look at the steepness of that geometry, they don't work very well. Maybe they improved now after version 1. The problem was that from the point of view of those classic optimizers, they look at the circuit, and the circuit is simply a black box of parameters. And so there's no structure in it. It's a lot of parameters. It's very hard to determine which parameters are in what relationship to other parameters and how to do the classic backpropagation through the circuit. But we have some other options. We have the linear and nonlinear approximation methods, such as Cobila, BFGS, which do not consider the structure of parameters. And in our case, we adopted the Cobila, and it worked quite well. So we've done a lot of experiments, and I have some actually numbers to show the performance of the training method. I decided to take it off because in the first approach with Qiskit, and the aim of the experiments was to denoise the time series and then use them for forecasting. And so we applied differencing to the data. That means we subtracted neighborhood values one from another. That's usually done so that in forecasting, the model does not try to echo the values which preceded the following value. And so the data was prepared differently, and encoding was differently, and the range of values would not be comparable with what we did later. But if you look at the structure of the time series recovered, reconstructed from the input, we can see the performance by visual inspection. So the blue line, both sections are in the validation data partition. That means this data wasn't used in training at all. The blue line represents the pure data, the original data in the time series. The orange line represents the noisy data. The noise was artificially injected around 10% of values. And the red line represents the reconstructed original value, original time series from noise. Of course, it's not original. You can see here that is the quantum method used. The shape of the reconstruction follows the noise. And here we have the classical PyTorch model in action. You can see the red line is better following the blue line away from the noise. But if you look at the statistics, both of them were nearly identical. So what we can say is that that particular quantum approach, it approaches the performance of the classical model. It's not exceeding it in any way. So there's more work to be done here in this space. It's interesting if you look at some numbers. This is the Qiskit state vector simulator, the Qiskit model, and this is the best PyTorch model. The Qiskit model required 180 parameters. The PyTorch model required nearly 10,000 parameters. The number of iterations for Qiskit was 2,000. In PyTorch was about 30,000. The speed of model training was 15 minutes for Qiskit and 20 seconds for PyTorch. So you think, wow, it's completely useless. But don't forget that we are working on a simulator, not a real quantum machine. If we consider the number of passes through forward and backwards through the model, the backward pass would be much quicker with fewer parameters than the backward pass with many parameters. If we could, the forward pass through the model would be running on a quantum machine, that would be a single tick. The same with PyTorch, a single tick. Of course, in quantum machine, you need to repeat measurements, perhaps 1,000 times. So we talking here 20,000 passes, that's 30,000 passes. It's comparable, and that's why results are comparable. There's a question here. For your anomalies, are they determined by being more than 3 sigmas, or are the anomalies based on the irregular shapes? For this particular experiment, we did not consider any anomalies. We simply considered noise. Okay, so anomalies is the next stage of the work. So here's just some showing the model, which could be useful for noise removal. But the idea is that if we could get determine what's normal. So maybe when you remove the noise, we get normal signal. Then we compare it against the original, and then we could analyze the difference, considering what's the noise, which is probably the regular noise, and then what are the spikes which go beyond the normalcy, and that could indicate anomalies. But that's a different project. Okay, so that was Qiskit, and there's interesting reflections that were done on this. So we didn't get great result. It was the Qiskit results were slightly better than PyTorch, slightly, but really not much difference. So this is an approach which relied on the variation quantum algorithms developed in Qiskit. The variation quantum algorithms basically is the algorithm which is based on parameterized circuits, and the algorithm is iterative, involving some execution on a quantum machine or the simulator, and some done on a classical machine, in particular the optimization. We could use the classical optimiser. Okay, you can hear me, because the host would like you to unmute.
It's been tried before.
Oh,
Sorry. I need to
mute myself. I'm working on 2 computers, and we had difficulties unmuting me. Something happened successfully. I unmuted myself on one computer. Okay. Okay, so coming back to the problems. One of the issues found to affect the training of the quantum model and its performance was dealing with deep quantum circuits consisting of large numbers of unstructured parameters. So that's something I referred to before. If you look at gradient-based optimizers, they cannot look inside into the structure of the parameters to perform something like backpropagation of weights. So that's one problem. The second is the large number of those parameters. And unfortunately, when you increase the number of parameters, the performance, the time required to optimize those parameters are not linear. So it's sort of like a quadratic relationship between number of parameters and the time required. So if you have a lot of parameters, you need to do a lot of weighting. And some short circuits were here 15 minutes each. If you run it 10 times to get, sorry, we have a hand up.
Yeah, because we have a question, but I will wait.
Okay, we have a question. Have tried different simulator and platforms. What was the results? Yes, so we Okay, so we tried working with Qiskit. Now we moved into PennyLane. So we use two different platforms. So we actually have, I'm going to discuss the differences between them. Qiskit is a very large community of people that use it. So if you get stuck, there's a lot of people who can help you out. PennyLane, which is based on Xanadu, it is based on Xanadu development. It's open, both are open source. There's a great community, a PennyLane community, but fewer participants ready to answer your questions. It's PennyLane was stable. The new versions are very consistent. In Qiskit, especially recently with IBM taking over the development, or much part of it, there's a lot of instability in software versions. And so I had real difficulties with Qiskit at some point in time. But for 2 years before that, I was very happy. As in both cases, I think that PennyLane documentation is much better. The recent developments into Qiskit, they made documentation obsolete. So we have a lot of tutorials which don't work anymore because of the rapid pace of development of the language. So IBM is moving into commercialization of that product. And so things are changing very rapidly. So we have to wait for Qiskit to stabilize a little bit. How does it impact Mike Hoke's theorem? I don't know. You may need to explain. Parameters are known or predicted. Parameters of the circuit are being trained. So they're being initialized with some random values, and that's why we need to do several runs with different initializations to get an idea of what's going to happen in training. And I'm going to show the variance of the impact of parameter initialization on the outcome in a minute. But let's come back to the problems and solutions. What PennyLane does, it allows you to impose layers over the structure of the circuit and identify the shape of the geometry of the circuit in terms of relationship of layers to layers. So which layer is closer to the measurement and its size, and what layer is away and closer to input. By doing so, when you start using the classic optimizer, the classic optimizer can use standard techniques like backpropagation because it knows how the information is propagated back and forth the circuit and how the layers could be optimized one layer at a time. Another possibility with PennyLane is to interweave classical components with quantum components. As long as the classical components, such as neural networks, are differentiable. That means you could calculate the gradients of the parameters. And that means that from the point of view of PennyLane, there's no difference between classical neural network and a quantum circuit. And a function like a sine, which gradient is known and could be calculated. And so you could create a large system of quantum and classical components into some kind of a hybrid system, which could be optimized in exactly the same way. So this is a very beautiful way of dealing with quantum approach, which is lacking in certain space. For example, the quantum circuits cannot embed nonlinearity. They are all linear systems. And if you combine them with the layers of a neural network, they could do the activity, layer, and you could inject nonlinear behavior in there. So it is possible to get the best of the two worlds. One great outcome of that is that if you could decouple, for example, a large quantum circuit into a separate encoder and decoder, they will only have half the parameters each. And so the training could be much, much more efficient. And that's what attracted me to Penelane in the first place. It's interesting that Qiskit recently adopted a very similar open source framework called Torch Quantum. It does exactly the same approach of layering parameter space in a circuit. Okay, so it seems much more complicated than Penelane, but it's available and it's actually advertised heavily in a community. So what would the circuit that we discussed before look like? And that's exactly what we implemented. So now we have two quantum components, which is the quantum encoder and decoder, separated by a thin layer of PyTorch neural network. It's a single layer. The measurement matches the size of this layer. And then on output, I have another layer of classical computation. It's a single layer of the neural network, which takes the input. It's interesting is that by injecting those single layers, the simulator got much better results straight away. That's because the optimizer could work much more efficiently. Everything else stayed the same. So it's a very small hybrid extension of the previous idea. So we have now shallow circuits. Might have fewer parameters, much quicker to optimize each, and we could actually inject a very large component of classical computation in the middle, and we could focus on where exactly is the value of quantum computation. For example, if you need to have the reversibility of computation, or if you want to generate a lot of possible outcomes, which could be done very quickly in using quantum approach. But since we decouple those two components of the large quantum circuit, we lose something in the process. What we lose is we transform the quantum information, the entangling information, into classical information, and we lose something in the middle. And if we were to run it on a quantum machine, of course, we run those two components separately, and we lose that connection, the quantum connection between those two. Perhaps in the future, we're going to get some different way of communicating between the two quantum components, and people are working on that. So Penelane and PyTorch, because we use both, they have excellent support for gradient manipulation, which is looking at the parameter space, the geometry, and looking how to descend down to the optimum point. And they offer several very highly efficient gradient optimizers. And we adopted the ADAM type of optimizers, the adaptive gradient momentum optimizer, and an Adam-Nesterov extension of the ADAM optimizer, which worked very, very well, very quick. Those are some of the results, which themselves give you a way to stop and reflect on what is going on, what's happening. Now, what we see here is, here we have experiments which looked at varying the number of layers in a circuit, so from 1 to 8. But we fixed the number of the split between latent space and trash, 5 qubits of latent space and 3 of trash. So the window was determined before to be 8. We experimented with Qiskit. What is the suitable window size for the data, which we used with beer sales? And then we have a range of experiments where we varied the split between latent and trash space while retaining the number of layers 3. We had actually we had the best results at 4. I think 3 was to make it compatible with what we did in Qiskit. I may need to rerun this experiment later. But and this is what was done on the classical model using PyTorch without any quantum components. All of the instances of the models were run at 1,000 epochs, 1,000 iterations in training. And I'll show you in a moment that that was enough for them to converge and in training, especially in the validation part, the test data. Just looking at this, we can see that if we vary the number of layers, the depth of the circuit, which actually increases the number of parameters, there is some optimum point, the optimum point beyond which results get better. So what's highlighted is the best results across different scores, different measurements. So those are the scores in training, and those are the scores in validation, which validation data did not participate in training. And the best scores in training were at number 4, layer 4 layers. The best in validation were at 5 layers. So the preference. So there is some kind of a preference for the size. Now, in our simulations, we did not consider quantum noise, which would affect the computation on the real machine. So we used a pure, not noisy simulation. And also, because we use the simulator using state vector, you don't need to repeat calculations 1,000 times in addition to make it slower. Okay, when it comes to looking at the split between latent and trash space, it is very clear that the models prefer to have as much space in the latent area as possible. So it seems like they want to have at least one trash space. So there is some kind of a redundancy on input, perhaps. The quantum model was very stable. They said, yep, give me as much latent space as possible. So it's actually interesting because a lot of people say really compressing input into much smaller space benefits the outcome. It benefits outcome because the model abstracts away from what's on input, and then you have a much better, purer result. That's a bit like the government say, we're going to cut funding to schools and it'll be more efficient. Okay, the same thing. We do not see it in data. We see that the models want to get as much space to optimize the parameters as possible without any barriers in the middle. We are optimizing the models on mean square error, but we calculate the scores in different areas. The MAPE, the mean absolute percentage error, is not useful for training, but it gives you indication what's happening in training. So it was by gaining additional insight into this. So that's interesting. We can see, we get some insights from this. And this is what happened if you look at the training curves. Now, each model was run 10 times to get some average performance on the model. That's actually a very important note to make. We cannot simply run a model and say that's the outcome. That's not is not what's going to happen. Just because we do quantum computing and quantum machine learning, it doesn't mean we don't do data science properly. So we need to collect statistics. We need to calculate the mean, the average outcome. Look at distribution of errors in this and variation. We do proper statistics here. So each of those curves, it represents the outcome of 10, which means that it costs you 10 times as much. In this loss of experiments, there was about 500 runs that we did at 1,000 epochs. And for quantum models, it would take about 4 to 5 minutes. So compared with Qiskit, it was about 3 times faster. So that's interesting. I actually thought initially it was 10 times faster, but when you look across different runs, that was about 3 times faster. That's because it's Pendelane approaches the simulation differently. On Qiskit, if you want to have high precision on a simulator using state vector, you had to still repeat the runs so many times, up to 1,000, and get high precision outcome. In Pendaline, you run once, and you get theoretical outcome of what the result would look like if you run it 1,000 times with high precision. It may have changed. I actually raised it as an issue with Qiskit, and I don't know if it was taken into consideration or not, but that was a serious problem that I could see. Now, looking at the training data and validation data, so those are the scores in training, and those are the scores in validation. They all, the cost function or loss function, mean square error in all cases. Each one 10 times run over 1,000 epochs. And you can see here different models, and we can see this is the logarithmic scale, Y scale, to see what happens at the bottom where the models are converging. If you look at what happens when we run it in PyTorch, classical model, we can see a lot of volatility at the bottom. So it may be something to do with the stochastic nature of that particular optimizer, but we run the same optimizer on in Pendaline. So there's no difference. In Pendaline, we have nice and smooth curves. So it's a Pendaline or quantum model has a linear behavior, and so it's more stable. We don't have this nonlinearities, which could produce those aberrations and those variations. So that's what we have here. The model was very predictable, and different runs were very consistent. So that was interesting, maybe good. I'm just saying that's what happens. Now, when it comes to the time of convergence within 1,000 epochs, it looked like in both Pendaline and PyTorch, the models could still do better. So they're pointing down, and that means that by giving more runs, they would probably get improve when it comes to mean square error in training. However, if you look at the run on the validation data, we can see they all plateau, and we can see the plateaus on much earlier than in Pendaline, so at 420, 700, 880. So we're not going to get much more generalization from those networks, even if we train them further. However, when it comes to quantum models, there's probably more space for improvement in validation scores. So we could probably get to 2,000 epochs. I'm going to do this experiment again, giving 2,000 epochs for each. So now, what about noise? Okay, so let's look at the way that the data is reconstructed, recovered from noise, and how it fits visually, at least, the data. For the little dots, they represent the reconstructed data. This is the synthetic data using a combination of trigonometric functions, like two sines interfering with each other. And this is the data, real beer sales data, real world data. And again, on training, we have a almost perfect alignment of dots with heavy blue line, which is the true curve. In red area, we have validation data not seen at all in training. And it's a pretty good alignment, much better than what happened in Qiskit. So that was quite satisfying. We can see that the model is, when we have a heavy volatility and peaks, sharp peaks, it likes to recreate the nice curves it found in training data. So perhaps we need to give more data, more training, more variation. We dealt here with a very small sample. Otherwise, we would not have time to compute it all. So the level of fit is much better. Here I show you also the variations between different runs. And with the bands, we show that within each run, when we consider 10 different instances, 10 different initializations of each model, we do have variations between them. So there's a band of variations for each model. So 10 different runs, and the results are in this band. Some of them are much wider, some of them are more narrow. I didn't show that for the PyTorch. PyTorch is probably much more narrow, much less variation between runs. Now, the big question is, first of all, any questions on this so far? Maybe later. Okay. Now the big question is, it looked like it's almost a classic autoencoder. We have autoencoder, encoding bit, decoding bit, the latent space in between, exactly like in a classic way. But can we utilize some features of quantum modeling which does not exist in classical approach? One of them is reliance on reversibility of quantum computation. So as long as we use unitary gates, that means we do not use initialization or the measurement. Most of the operations, the standard operations, are unitary, and the combination gives you the outcome that the computation is reversible. That means you could prepare the adjoint of the original model. Of course, by sticking some measurement in the middle, we're going to upset that. But looking at just the decoder. So this is the standard sequence of events: encoder, latent space, decoder, noise, and pure data. So if we could take decoder and invert it, reverse it. So we could put it in the middle. We could then stick what we expect on output as input, and decode it. And what we can do is, if we train this decoder so that it decodes exactly what's on input, it will learn to deal with or to compress pure data into latent space. Now, what we can do is to do a trick here. If we could train the decoder on input in such a way that we try to converge the trash space to zero, that means all useful information will appear in latent space. So we can train this half autoencoder separately so that it learns to compress good data, pure data, into latent space, and as little data in trash space. So we train it separately. Now we can invert it. So use all the parameter values, optimal parameter values here, freeze those parameters, put the encoder with untrained encoder, and then we could train it, just that component, this is already trained, to deal with converting noise into compressed pure data, because that's what we expect this will do. So the convergence between those two will be the second run. So it's an unusual way that cannot be done classically at all, because classical computation is not reversible. We could do another little trick. If we train the decoder first, what we can do, so if, for example, the trash space is little, that means training this component on converging to zero is very, very quick. But it could be that the latent space is very small, in which case what we can do is to converge not on the outcome, but on having the two decoder and encoder latent space meeting together. And so I call it a sidekick approach. So we could have a model which you could train different components of that model separately and then putting them together and retraining. One typical way of dealing with barren plateaus, for example, is to train the model using special techniques which avoid barren plateaus. You get a set of good parameters, then unfreeze them, and then retrain it again, hoping that when we avoided barren plateaus and got very close to the optimum, then we need fewer iterations to get to the optimum, and close to the optimal, hopefully we don't have barren plateaus. The barren plateaus are the flat areas of the loss function where the optimizer cannot find any gradient down. So the gradient is 0 and it's looking everywhere, circling around, and cannot find any dip to look for the optimum. Now, what happens with quantum models? The more parameters we have, the multidimensional space gets flat, which means that from the optimum, it's almost the same distance to all points on the surface of the loss function. So that's actually a problem with both neural networks, but classical neural networks, but especially in quantum models. If you have a very large circuit, it's very easy for the circuit to get stuck in a gradient plateau. Sorry, in the barren plateau. So there is a benefit of splitting your computation into smaller fragments. And there's I wrote a paper with my colleague how to deal with barren plateaus in quantum modeling, which can be found from my website. Okay, so summary of this. So model design insights. We discussed a variety of design decisions which can be taken in development of complex quantum models. In our case, the quantum time series autoencoder, which can deal with noise on input and removing that noise. So input encoding strategy determines what ansatz can be employed and vice versa. So we can't simply take ZZ encoder and then use ansatz which relies on encoding of in a Y rotation. So they need to be compatible. So you need to do a bit of study of what encoding strategy is good for the ansatz. What encoding strategy will determine what ansatz we should be using as well. The methods of measuring and interpreting a quantum state of the circuit impacts the choice of the loss function. So in fact, if you look at some theoretical papers, they basically they take the measurement of the circuit and they treat that measurement as a loss function. That's why we have a global loss function and local loss function, depending how many qubits we are measuring. But it's more complex when we deal with classic optimizers as well. So definitely the way we measure and interpret the results, which is related to the quantum state, it will determine what cost function, loss function is suitable for training the model. So we need to do a bit of experimenting as well. Then ansatz architectural properties, which I just discussed a moment ago, they must fit the model aim and function. Okay, so if we simply have pure data and all we want is to compress it and then decode it, then half encoder is just enough. Okay, if we deal with noise, we have two-stage training. Or if we have a very fast machine or we run it on a quantum machine, we could use a large circuit, but then we have to deal with noise and use some error mitigation strategies, because that's likely to happen. The large circuit will decohere halfway through the training. Ansatz width, depth, the number of trainable parameters, additional degree of freedom like extra qubits, and data used in training, they all influence the success of the optimization. So it can't simply assume certain structure, run it, get the outcome. You need to perform a lot of experiments. That takes time, a lot of time, especially if you run it on a simulator. If you have access to large data centers with NVIDIA accelerators, that's fantastic. Okay, so I run it on my big gaming machine, but it's nowhere near as good as running on a big accelerator or multiple GPUs, for example. And that costs money. Selection of a suitable cost function and optimize the required experiments. I mentioned that. Now, when it comes to performance insights, the assessment of the model quality requires not only statistics, but also suitable theory. Okay, so it seems to be that most of the assessment of quality is boiling down to your training curves and validation curves if you're lucky, because a lot of people don't even bother. There's other ways of measuring quality of your model. So one of them is to look at the capacity to learn. So model capacity to learn is it's separate from training. It's related to training, but separate from training. So you could actually measure the model geometry. You could actually look at the geometry of the parameter space. And from this parameter space, you could determine upfront, before the model starts training, whether it has capacity to learn. Okay, and what is this capacity to learn? How does it compare one ansatz versus another ansatz? So you can perform analysis before training, just looking at the random parameterization of the ansatz structure. And then you could look at the geometry and the gradient space, for example, to determine if it's the space is concave or not, because that will affect training. Okay, so that's actually interesting. You need to have some theoretical approach to dealing with the models and assessing the model's ability to support complex training. Now, the pure quantum models are merely approaching the performance of classical models, at least in quantum autoencoders. You need to find yourself a niche of where the complexity is such that the quantum models could help. On the simulators, the hybrid quantum classical models perform better than either pure quantum models or pure classical models, and you could get the benefit of the two. The hybrid models use the quantum efficiency when trained and executed on quantum machines. That's what we expect to happen. You can't break the system down and hope that it will then behave as it was one piece. The quantum models can take advantage of the model features absent from classical systems, such as reversibility of them, or such as dealing with exponential size of the parameter space, of the outcome space. And hybrid models, in turn, could inject the model features missing from the pure quantum system, such as nonlinearity, for example. So there's a lot of options you need to deal with. Now, what we do, we look at tighter integration between classical and quantum methods. So I'm a great believer in hybrid approach. Eventually, whatever quantum solution you're going to get, it will address only some part of the problem. And you need to surround it with classical computation, preparing data, getting the data out, using it as part of the large commercial system, perhaps. Investigation of different architecture, the quality and effectiveness, that's what we're looking at. And I'll be writing a paper on this. And then moving beyond noise, in particular, looking at, can we use those techniques to detect anomalies, perhaps detect chaotic behavior as well, and predict those behaviors. And also moving beyond quantum autoencoders, maybe into quantum generative adversarial networks or quantum transformers, which now is a trendy option in machine learning, but also to give you a lot of interesting scope for putting quantum machines into part of the equation. And that gets us to the end. I have a couple of slides in the appendix in case you wanted to find out more about what's time series analysis and what are quantum neural networks. But if you have any questions, you're welcome to ask.
I noticed there's a question from Dr. Itama. He asks, parameters are known or predicted?
Sorry, didn't understand.
Dr. Itama asked a question. Parameters are known or predicted?
Parameters are known or predicted. The parameters are not known upfront. The parameters are being trained. So what happens is that the parameters are part of the ansatz structure. And the ansatz is the trainable part of the quantum model. And usually we initialize those parameters with some values. And so we could initialize them with 0, for example, but that gives you better training outcome. We could initialize them randomly. And some people say that random initialization can encourage barren plateaus. So there is actually the whole art of avoiding barren plateaus. There's about 6 different ways of dealing with issues in trainability of networks. But parameters get trained, and eventually, once you get the optimum set of parameter values, you could fix them, and then you could apply them to new data. So parameters are not known in advance. They're not predicted. They're trained.
And I also got a question earlier from Jervis. He asked, what paths do you suggest to optimize your quantum modules?
What, sorry?
What paths do you suggest to optimize your quantum modules?
What parts? I get a very bad speaker on my laptop, so I don't hear you well. So that's the structure of the circuit. When it comes to quantum autoencoder, so we have the several layers of encoder and several layers of decoder, and those rotation blocks, they consist of 3 rotations in X, Y, and Z axis on the block sphere. So we could change the state of each qubit by setting its rotation. So in training, what happens is that the optimizer is going to vary those 3 values. So basically, each operation, it adds 3 parameters to the parameter space of this model. And the classical optimizer is varying those values. So this is like in a neural network. In neural network, you have layers, the interconnected layers. Those layers have weights, and the weights get optimized. So those rotation blocks basically consist of weights of this model, and the weights can be parameterized. You could actually add biases as well. So the model will be very much like a classical neural network from the perspective of the optimizer. The optimizer is going to look at the quantum model, can see the layers, can see the weights, and possibly optionally the biases as well. And then we have from the perspective of a classical optimizer, this is just a neural network. Okay, we have paths. Oh, paths. What paths?
This is for this question before.
Okay, so the question is, what are the paths that can be parameterized? If you could repeat the question again.
What path do you suggest to optimize your quantum modules?
Okay. You mean what approach?
I don't know if we have.
Yeah. I'm not sure if I understand the path here. When there's no path through the circuit, because the circuit will not have a path. Imagine this is just Itamar asking a question. When it comes to what approaches we could consider for model optimization, that's actually a really good question, because you could actually use a purely quantum approach to optimization, and then you could take a classical optimization. So in a purely quantum optimization, what we can do is to, like in those of you who are familiar with Grover approach, when you have blocks of Grover blocks and you multiply them, we get a similar approach to annealing. So it's a quantum annealing, and you could use that effect to amplify certain signals or to sort of optimize the circuit in a sense by replicating blocks, and in a sense that's equivalent to optimization. So a lot of quantum optimization techniques rely on that. It's a purely quantum approach. It's not outside interference with this. You can also use a purely quantum loss function. So for example, if you wanted to add a layer at the back, I'm going to show you what happened before. Okay, so here there was a pure quantum approach. In training, we had some input parameters and coding data, but at the back, I put the inverse of the encoded data so that we could train the network, the whole circuit, expecting 0 to emerge at the end. So if we provide input and reversal of output, so they should cancel the input. If this middle is going to give a perfect result, what was happening on output or what's expected, that means the 0 should be expected on measurement. And that 0 could be very easily measured by providing a few gates, quantum gates. So we don't need to, in such a case, have a classical optimizer. You could simply optimize it on expected 0 on output. So that's another approach of doing it. But once you're in penny lane and you have a purely hybrid approach, you could rely on very well-known optimizer techniques like Kobla was in Qiskit and Nadam was in penny lane. But yep, we have options here. And one thing I found is that unfortunately at this stage, the classical optimization techniques are very good, and the quantum approaches need a lot of work. So things like how you determine there is a 0 at the end. Do you simply have so-called swap gates and look at a single value, or do you look at probability of 0 at each quantum separately, or looking at probability distribution and measure a single combination of 0, 0, 0 in probability distribution? And each one will give you a different outcome. And so that's actually, there's a lot of debate in the community how to do a proper quantum optimization of circuits and quantum loss function. Now, one thing, Itamar is asking a question. Yes, you have a hand up.
May I ask?
You have asked, okay. Okay.
May I ask you a question?
Yeah, sure, go ahead.
Okay. We talk so much about optimizations, and you have shown very beautiful techniques that I still have to learn. But I wonder, in the practical optimization problems, there is huge number of variables and huge number of constraints.
Mm-hmm.
And the question is, maybe some of these can be solved better than the commercial packages like Gurobi and the other ones that I forget now the name, but there are several big commercial packages that are very expensive as well. Maybe some of your techniques can contribute for people without budget to solve big practical problems.
Yeah, no, thank you for this question. I agree, that's the future. At this stage, unfortunately, the state of quantum machine learning and as supported by quantum machines Most of the work in this space is research. Okay, so I don't think that at this stage a lot of quantum machine learning is going to get into production easily. The most successful area is chemistry and still only on very small molecules. But we do have, actually, when it comes to quantum optimization, there's some techniques which have been developed and they're very successful. A lot of techniques, they use the so-called the Ising model. So they put the quantum layer and transform into behavioral qubits. And they work very well. Okay, so the transition from classical approach to quantum approach sometimes is smooth, and you could gain some advantage from future generation of quantum machines. At the moment, one of the issues you mentioned, we talk about thousands of parameters. Thousands of parameters will require thousands of qubits, and people like IBM, they can deliver machines which have hundreds of qubits. The problem with computation on those machines is that once you put a circuit on 400 qubits, the probability that one of them will give you bad result or there's a decoherence happening on some of those qubits is very, very high. So at the moment, most of the work with very large circuits, it's pure research, basically how you deal with errors in there. And so a lot of work goes into error mitigation, and it's not easy to translate what you see in front of you here into a similar circuit which has 100 qubits encoding thousands of parameters. That is not happening anytime soon until the manufacturers deal with error correction. Okay, so, but development is very fast. We have a lot of new technologies coming in. We have photonic machines. We have diamond-based machines. Some of them operating in room temperature. So it's happening. Maybe we're going to get eventually some machines, topological quantum machines, which will be highly reliable and error-free. But the development in this space is huge, and marrying the two, the machine learning with quantum, it has tensions. It's not easy. We need to develop new algorithms which are quantum based rather than simply adopting classical algorithms of quantum machines. So that's happening. It's research.
Okay, thank you.
Thank you.
Okay, do we have other kinds of questions?
There's a question earlier. It's on YouTube. How does this impact Mike Hawke's theorem?
I'm not sure. I'm not familiar with Mike Hawke's theorem. Sorry about that.
I am also.
Yep.
So if someone can say what it means by Mike Hawke's theorem, because it's hard to even search it on.
Yeah, I'm not familiar with that. I'm sure that it impacts a lot of theorems, and at the moment, it's a difficult, the whole area of quantum machine learning. It's difficult. So some of you, those of you who just started in quantum computing and find it difficult because it involves linear algebra and a lot of maths. Now, quantum machine learning, it adds additional complexity. We talk about partial differential equations, and so all the optimization aspects, the gradient spaces, the multidimensional geometry, how you deal with those geometries, how you model it, how to determine the shape of this geometry, if it's suitable for optimization or not. It's a lot of interesting work, and that's extra maths. So myself, I used to teach machine learning and basically analytics, predictive analytics. That was my area. So it was more comfortable for me to move into quantum machine learning. but it's a hard maths. Now, those of you who are coming from physics background, you're all laughing. So physicists should be kings of quantum machine learning because they're equipped to deal with all the mathematics in this space, like my good friend Sebastian.
Yeah, exactly. Okay.
I have a question. I have a
Okay.
question.
Yes.
Yeah. So, do you know how many company or people are working on this topic about quantum autoencoder? So, how far they are, which difficulties they are facing, and what advances they have made, and yeah, that's my question. And also, have you tried using classic platform for this project?
Yeah, so I actually gave examples of experiments using a purely classical solution. So
no, I'm not talking about the classical quantum mechanics. I'm talking about there is a platform called a quantum platform called Classic.
Yeah.
Okay, yeah, that's what I'm talking about. Thank you.
Okay. First of all, a lot of work in this space was done with time series analysis, and there's very few people who do work on using quantum computing approach to time series analysis. So we talk about dozens of those people. Among those dozens, when it comes to quantum autoencoders, it's a handful of papers published in this space. Most of them are not on time series analysis. So it's very little work in this area. And I asked myself, why so little? And one of the answers is that because classical methods in time series analysis are so advanced that perhaps it's not needed, perhaps it's not. But we're looking at some cases where the complexity of anomalies is very high. So, for example, if you look at the issues on the stock market, and the stock market crashes very slowly. Okay, so stock market crashes. The imminent crash happens like 48 hours and spreading around the globe slowly. But the signs of the stock market crash could be traced weeks before. And it's only after it crashed we could find out that some events happened much, much earlier. This is very complicated, and we can investigate those situations only after we have a catastrophic event happening. But because of this complexity, maybe the quantum approach, which is excellent in dealing with complexity, could be better suited. That's what we're looking for. We're looking for very complex nature of anomalies rather than something happened quick. Sebastian would like to say something.
Yeah, because this question was connected strictly with what I start to say, that and if you can take some comments about this, that we start from time series data, but of course we can use autoencoders for any kinds of data. So what do you think about using these kinds of autoencoders for other kinds of data? And this will be the next steps and how we can use it on the market or in the businesses.
Yeah. So absolutely, the time series is just difficult to deal with. Okay, and there's you really need to look at the nature of data we're dealing with. One of the interesting things about time series is that if you look at the data values in the neighborhood, there is some kind of a continuity there. So you could actually rely on that as well in the processing. But then you could look at alternatives like we could look at convolutional neural networks because of the neighborhood, which is meaningful in the time series. Now, when you look at tabular data, absolutely, everything I talked about today, it will support tabular data where each qubit represents a different variable. That's not issues. We make no assumption in any way that there is either continuity of values of the neighboring values within the window. We almost treated it like independent variables. However, because the windows were overlapping, when it came to the final outcome, when you collapse the data back from individual windows to the continuous time series, you gain some advantage because there's a bit of averaging of different results on output.
Yeah, and there is just one a special case which probably everyone use today, autoencoders. It's called NLP. It's a transformer where you use your ChatGPT, you use kinds of autoencoder. Yeah. So this was the main thing that we should start from autoencoders because it's very, very important today for any kinds of ChatGPT systems. Yeah, so and any kinds of transformer models. So you see, it's there is a lot of possibility how to use these kinds of modeling. And what is the nice is that you probably will get maybe not better models like classical transformers, but you have a less of parameters. You have a maybe simple, maybe not so huge with not so huge model with not so huge no deep model and no many qubits model. So this is a path that we want to go and check this kinds of possibility. Yes. So
yeah, so that's actually a very interesting space, and the transformers and the step between autoencoders and transformers is actually, it's a large step. The same with GANs, but GANs have the issue of latent space and how the latent space could be used to generate outcomes for generative models. And this is actually another thing is that if you look at generative models, the efficiency of the generator is very important. And this is where quantum techniques could help. You get true random outcomes, and generators you could produce a lot of distributions of required shape very, very efficiently. So that's with GANs, that's another application. But the transformers and the self attention. So we need to look at how we could create the encoder, quantum encoder for the transformer, and then how you do transformations. And the transformer, which is the large language models, this suits very well time series. Just because they use words and sentences, it doesn't mean other types of sequences cannot be used. And people do that very, very effectively. So it's another space. I'm interested in time series and signals because they are very difficult to deal with. And we treat this exercise not only as finding a solution which will be give you advantage, but also finding the problem that we can learn how you deal with developing algorithm for that classical problem in a quantum way. It's a different type of thinking, different approach, and it's a learning exercise as well. It's learning exercise, and it's worth sharing your insights in this space.
There is something I don't understand is that how can I know there is some algorithm they cannot work? Like, yeah, my question is there is some algorithm classical computing, and they cannot work in quantum computing. And my question is, how do you deal with this kind of problems? Thank you.
Well, that's why I'm a great believer in hybrid models that you could. I don't think that quantum computing is going to replace classical algorithms, none at all. But what you can do is to find your problems where quantum solution is going to add value. So definitely you need to be able to judge, is it suitable for quantum algorithm or not? There's a lot of quantum inspired solutions. That means some of the techniques we develop for quantum machines, now they're being translated back into classical approaches with a twist. I think that we get a lot of synergy between the classical solutions and quantum solutions, and we learn from each other camps. So I'm not necessarily looking at replacing every classical algorithm with quantum algorithm. It's not possible at all. But we can learn from each other and then find improvement. So that's why we moved into Pendulane, because Pendulane gives you this fantastic ability to combine your quantum elements with classical elements in a consistent framework that could be optimized together, especially in machine learning.
Yeah, we have another question. How will the new breakthroughs in quantum error correction affect quantum computing?
Well, there's so much working in error correction. And one thing is that when we talk about error correction, people have very vastly different approaches with different type of hardware architectures. So they have unique to different architectures. There's generic approaches. Definitely, when we talk about large circuits, large models, if you want to run it on a real machine, you can't do it without introducing error correction and error mitigation techniques. There was actually last year the whole IBM quantum challenge, Qiskit challenge, which was fully devoted to error correction on large machines, large circuits. It can't virtually do anything on those large circuits without a serious approach to error correction. So in our technique on a simulator, you could say, let's deal with this as if the machine was error-free, noise-free. That is not going to happen for a while. Okay, we have how will the new breakthrough in quantum error correction affect quantum computing? Well, we have a lot of breakthroughs, so I'm not sure which one and for which machine type, but there is it's a massive amount of work going into error correction. So there is a lot of approaches. So if you look at Qiskit, by default, once you submit your circuit for execution, you need to pick your optimization technique that will already could inject error correction in it. A lot of this happening on hardware level as well. Flagged weight optimization. So yeah, I'm not in the area of error correction. I've done some of the tutorials and some of the quantum challenges with error correction, but yeah, it's not my field. There are people who spend their life coming up with the new approaches to it. So don't know this particular approach. I hope it comes out of the box. You could say, flick it on, click, and it happens. I think at this stage, if you're looking for the career in quantum computing, this is the place. One of the issues is in quantum engineering, in hardware development. Everybody's in this space, including Australia. Even the government paid $1 billion for C Quantum to establish the manufacturing site in Queensland to create quantum machines. The next one would be actually error correction, but also cryptography, networking, security. big space, but it's not my area.
Okay, so do we have any more questions, remarks?
Well, I hope that this was useful. One thing is that if you were looking for a copy of today's presentation, let me just get.
Maybe Jacob, you can put it to our chat. This links.
Yeah. So if you go to my website, hang on, I am on. Okay, let's see if that works, because I'm having issues with connection. Where's my chat? Chat. Okay. It's easy to remember. That's my website, jacobcybulski.com. And if you go to presentations, that's the one. At the top, you can see here, development of quantum encoders. Today's talk is a PDF. And those are the slides for today. So if you're interested in some of the publications, recent publications, you can also find in that on that website. So for some reason I can't do this.
Yeah, we put this address to the chat, so don't worry.
Yeah, so then you could find the slides there, and if you have any questions, send me email. You could find me on LinkedIn as well, and so please do ask questions and invite me. I'll be there.
Okay,
Thank you for your attendance. It's great to have so many questions, and hopefully we'll see you again.
Okay, thanks, Jacob, for your talk. Very interesting topics, and so see you in the next our meeting.
Thank you for coming.
Thank you.
Thank you. Yes. Goodbye.
Bye-bye.